Hi, welcome to the last week of lecture video. This week we're going to cover antiderivatives, area, distances. Then we'll cover the very important theorem called the fundamental theorem of calculus. Okay, let's start by talking about antiderivatives. We've been talking about derivatives for a while now. And so here's the definition for an antiderivative. Essentially, if you have a function f, big F, whose derivative is the function little f, then the big F function is called an antiderivative of the little f function. And so again, the big function f is an antiderivative of little f on the interval I if when you differentiate the big F, you get the little f on that interval. So this is a good example. So here, little f is x squared. And notice that this is a whole family of big F. In other words, these are all the different antiderivatives of little f. For example, you look at this one right here. If I differentiate this, the power rule, bring down the 3, subtract 1, I get little f, which is x squared. Now, if I take that function and add a constant, then when I differentiate it, it's still going to be the same because when I differentiate the constant, that goes to 0. So all these functions all differentiate to x squared, and notice that they all differ by a constant. So once you find one antiderivative, all you have to do is move it up and down by some constant to get a whole family of all of these antiderivatives. And so that's basically what this theorem says. If you can find one big F, one antiderivative of little f on some interval, then you can find all of them, or the most general antiderivative, by simply adding a constant c. And c could be any constant. Yeah, let's do some example. So for part A here, the little f is sine of x. So I'm looking for the most general antiderivative of sine of x. And again, if you know your derivative, then you can find the antiderivative by just simply thinking backwards. So for example, if I differentiate cosine, I get negative sine. So I put a negative in front of it. Then I get that if I differentiate negative cosine, I get sine. So thinking backwards like that can give you one antiderivative, and then adding the plus c will give you the most general, or the family of all of them. Part B is a bit tricky. Turns out that the most general one is actually ln of absolute value of x plus c. So if you remember from the previous section, when I differentiate ln of x, I get 1 over x. But the most general one is the one that has the absolute value of x. If I put in absolute value of x and I differentiate it, I also get that the slope of this function, you can, one way to check this is to kind of graph this out on the calculator and check that when I differentiate that general function, I get 1 over x. So that's the most general one. And then lastly, this is just basically trying to find, this is basically the reverse power rule. The power rule tells us how to differentiate something like this. If I want to find the antiderivative, I gotta just reverse the power rule. So remember, the power rule says that to differentiate something, you bring down the power and subtract 1. And so the way we reverse that is to say that if I differentiate this function in particular, x to the n plus 1 over n plus 1, the n plus 1 comes down, cancel with this, and then after subtracting it, you get x to the n. And so because of that, the most general antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c. So again, to anti-differentiate the power rule, you add 1 to the exponent, and you divide by that new exponent. which is the reverse of bringing down the n, subtracting 1. So again, add 1 to the power, divide by the same constant, and then add the plus c. So this is basically the table of all the anti-differentiation formulas. And the one we saw just now is the power rule, which is very useful. Again, if you have a power rule, as long as n is not negative 1, then you add 1 to the power, divide by n plus 1. Notice when n is negative 1, you cannot do this because if you add 1 to negative 1 and then divide by it, you're dividing by 0. So this rule doesn't work for the case where the power is negative 1. But we already knew that because when the power is negative 1, that's the same thing as x to the negative 1, which is 1 over x. And we saw the early example that the most general antiderivative is ln of absolute value of x. For e to the x is the same as ex. For b to the x, where b is not e, it's the same as b to the x, but you have to divide by ln of b. And then for cosine is sine, etc. And so, and on the right side, for example, again, all these just thinking backwards. If I differentiate secant, I get secant tangent. Therefore, the antiderivative of secant tangent is secant. Same thing for inverse sine, inverse tangent. You don't have to worry about these hyperbolic sine, cosine. So don't worry about that for this course. So here's another one. Again, trying to find the g so that g prime is this. In other words, we're trying to find the family of all antiderivatives of g prime. Notice this is, if I break this apart into two functions, it's just a power rule. So let's first rewrite g prime by breaking this into two power function. This over x, and then root of x over x. And then simplifying that will give you this. So this is g prime, simplify, so that I have two power rule, and I can apply that rule that we saw, the reverse power rule. And also we know that when you differentiate, cosine is negative sine, so you need a negative here in front of it. So again, you can always double check. If I differentiate negative 4 cosine, I get 4 sine. And then the rest of this is just the reverse power rule. The 4 here, add 1 is 5, divide by it. So 2x to the 5th divided by 5. 1 over x, root of x, rewriting it is x to the negative 1/2. Right? Root of x is 1/2, so you bring it on top as negative. Again, applying the power rule, add 1 is 1/2, divide by 1/2 is the same thing as multiplying by 2 in front. So you can check that this is the g of x. So in this example, we found the general, the family of all antiderivatives, which has the plus c. I can find out the particular c if I have some more information. If I have 1 point, I can actually figure out what c it is. Let me explain that again. Let me go back to this one. Notice that again, the antiderivatives of x squared has there's a family of them. There's a bunch for one for every c. If I want to find a particular c, then I need more information. If I have 1 point, if I know that my particular antiderivative passes through a particular point, then that actually determines the c. So for example, if I want an antiderivative of this that passes to this point on my mouse, then it has to be this this black function here. And so that's what we're going to talk about next. Is that I can solve for a particular c if I have some information. If I have a point, then I can actually find that c. And so trying to solve these kind of problems where we're given a differential equation, a differential, and we're looking for g of x that satisfy that differential equation, is basically what we'll talk about. There's actually a whole course that you can take at UMass Boston that will cover this kind of problem. What we do here is just a simpler version of this. So we see that here. So I'm trying to solve this differential equation, this f prime. Again, that will give you the general f. But if I have an additional point, then that can help me find a particular solution. Okay, so let's try that. So the most general solution, f, we can just rewrite f prime to be like this. I notice that the antiderivative of ex is ex, and this we recognize to be the antiderivative of this to be inverse tangent. If I differentiate inverse tangent, I get exactly this. And so this is a plus c. So that's the general version. If I want to find a particular c that satisfies this particular point, then I plug in this point, and I can find this c. So if I plug in 0, I should get negative 2 on the one hand, that's given here. But if I plug in 0 into this general antiderivative, I get this is 1 plus this is 0 plus c is negative 2. And so if I solve for c, I get that c is equal to negative 2 minus this 1, so it's negative 3. So again, if I plug in 0, I can find the c that satisfies this particular point. So once I find that c to be negative 3, then this is my particular solution. So this above here is the general solution that has the plus c. If I have a point, then I can find a particular solution. This is one solution, one function only, whereas this is a family of functions. This idea is useful whenever we analyze motion. Remember that if we have the position function, we can find velocity by differentiating. If I differentiate again, I get the acceleration. But what if I were to reverse that process? What if I only have the acceleration function and I want to find the velocity function? Or if I have the velocity function, I want to reverse that to find the position function. Reversing that is anti-differentiating. And so let's see an example of this. Suppose we have a particle that moves on a number line left to right. So we've seen this before. And suppose that we know the acceleration. So again, earlier we know the position. We differentiate to get velocity and acceleration. But now we're reversing this problem. I know the acceleration, and I want to reverse this to find velocity and position. Let's say that I have some initial data. Again, I need to know some initial points to pinpoint exactly the particular c. Let's say that my initial velocity is negative 6 centimeters per second. And my initial plate displacement, my initial position is 9 centimeters. So let's find S of t. So first we have to find, so if I know A of t, I can reverse it to find V of t. So again, differentiating V gives me A, so anti-differentiating A gives me V. So I use the reverse power rule, take the power 1 here, add 1 divided by 2, and then the antiderivative of 4 is just 4t, again, same rule. Then there's a plus c, and after simplifying, here's the general v of t, the general velocity function. If I want to find the c, I have to plug in the point v of 0 at negative 6. So if I plug in 0 for t, I should get negative 6. And then that should give me that c is negative 6. So this is my particular solution. But I need my position, so I have to do this again. So to do this again, I have to find the antiderivative of v of t, which is the position function. So again, applying the power rule, here's add 1 divided by that. So add 1 is 3 divided by 3. 1 plus 1 is 2 divided by 2. So if I do that, I get this general S of t with a plus d. And after simplifying, I have the general solution for the position. And then to find the particular d, again, I plug in the initial condition here. I plug in s of 0 to be 9. If I do that, I can find, I can solve for d. I can plug in 0, the right side here, this side only have d, and then we know that d has to be equal to 9 because we're given that information. So this is the particular solution, S of t. This is the position function that satisfies these conditions. Okay, let's talk about area and distance problems. in basic geometry from high school, we know how to find areas of simple things like a rectangle, a triangle, or a polygon if we can divide up into a bunch of triangle, each of which we can find the area. And then we can add up all the areas. So adding all these triangle can give us the area for the general polygon. But that doesn't help us find something like this. What if I want to find the area of something that's given by a curve and not by these straight lines? How do you find the area of this? So this is kind of basically the second major question that can be answered by calculus, which we saw earlier is kind of basically given by the process of anti-differentiating. So the problem of the solution to this problem, finding the area given by a curve, turned out to be a major theorem called the fundamental theorem of calculus, which is basically just using anti-differentiating, which we just talked about. So antiderivatives will be used to actually solve this problem. But that's kind of a little bit ahead of ourselves. That's a little bit later on. So let's kind of figure out how to do this from scratch. So one way of doing this is to kind of break this down, just like the motivating example here is to break down to a bunch of shapes that we know how to find the area of. If I break this down to a bunch of rectangles, I can approximate this area. So for example here, I'm using 10 rectangles. And the rectangle's area is a little bit bigger than the area under the curve, the function, but this is just an approximation. And notice if I have more rectangles, say 30, then my approximation is better, right? That this rectangle overshoot only by a little bit. And the more rectangle I have, the better the approximation. And you can kind of imagine this process repeating over and over again. We saw this earlier in the class, taking a limit, right? If I take a limit as n go to infinity, where n is the number of rectangle, as you have more and more rectangles, as the number of rectangles increases, that limit process will give us, turns out, the exact area. And that's how we use calculus to find this area exactly. Okay, so let's kind of break this down a little bit further. So again, the idea here is that I'm going to approximate the area under the curve by using n rectangles. So this is R of n. And so the first rectangle is just delta x. That's what this delta x is. It's just this width right here. And notice delta x here is the same throughout all the rectangles. So how do you find delta x? It's just the width of the entire interval, b minus a, divided by the number of rectangles that we use. So that delta x is always the same. The width of every rectangle is always the same. How do you find the height of the rectangle? Well, it's just the function evaluated at x1 for the first rectangle. So f of x1 is this height. That height, and along with the width, gives you the area of the first rectangle. I do this again for the second rectangle. F of x sub 2 gives you the height, times the width gives you the area. And I add up all these areas of all these rectangles all the way to the last rectangles. Then that provides an approximation of this area under this function. And if I can repeat this over and over again for more and more rectangles, then I get the exact area. And so that's how we're going to define this area under the curve, is that we find the area of n rectangles, and we take the limit as n go to infinity. As n go to infinity, there are more and more rectangles, and the approximation gets better and better. This limit, if it exists, is going to be our definition of the area under the curve. There's a shortcut notation using sigma notation if you want to do a shortcut. But for this course, we won't have to worry about this. Yeah, this example you're welcome to look at. It's just an example of looking at approximating the total distance if you know the velocity at a certain points here, finite number of points. You can look at that again, but that's not going to be something we'll be testing. So this is an optional slide. Okay, now let's talk about definite integrals. So earlier we talked about this whole limit process of finding areas of rectangle, approximating it, and then taking the limit, and that limit would be the area of the under the curve of our function. So we're gonna come up. So that process, we're gonna give it a name now. We're gonna call this the definite integral. So the definite integral from a to b of this function. This is the notation. Notice the notation is kind of similar. The sigma is replaced by this integral symbol. The dx is replaced by delta x. So this is the definition. This definite integral represent exactly this process of finding area using n rectangle and taking the limit. Now this definite integral, again, something that you won't be tested on, but this limit, the way it's defined, only exists if whenever we take this limit, there's a whole sampling process where you have to pick a point. Earlier here, notice I picked the right endpoint, right? For every rectangle, I look at the right endpoint in that width, and I look at the height. For every rectangle, I look at the right endpoint. For this definition to make sense, we have to make sure that this works for any sample point, not just the right endpoint. If I were to use the left endpoint, it should also be the same. This limit process should not depend on which point I use, the endpoint or even the midpoint or any random point in that interval. Again, something we don't have to worry about. So don't worry too much if that's not clear. So all we want to understand from this is that I find the area of n rectangles, which is an approximation to the area. I take the limit, and if that limit exists, that number, which is the area under the curve, is exactly the definite integral. In other words, the definite integral from a to b of this function, by definition, again, this is definition, is exactly the area under the curve, under the function along the x-axis. And if this limit exists, then we say that the function is integrable. So again, all we want to think about this is that this symbol represents the area under the curve. And this is called the definite integral. And it has some nice properties. For example, if you try to find the area under the curve of f plus g, you can find the area of them separately and add them. If you try to find the integral, the area under the constant function c, you look at this. This is simply just the area of the rectangle. If the function is horizontal line, then the area under the curve is just the area of the rectangle. Constant can be pulled out. The definite integral of the difference is just the difference of the definite integrals. But again, so far, the definite integral just represent the area under the curve. So for example, if you have a curve like this, here's a function, here's a straight line, and then the second half of that function, this is kind of a piecewise function, it's just simply this semicircle. And so what's the definite integral from 0 to 7 of this function? Given by this blue and red curves, well, just the area between the function and the x-axis. That's just the definition of this, right? So forget about the whole limit and all that. That whole limit process, in the end, just give us the area. Because these curves gives you a nice shape. This is just a triangle. We know how to find the area of that, so we don't have to worry about finding the limit and any of that stuff. This is just the area of a half circle. We know how to find the area of that. So whether we do it by limit or not, it's going to be the same. So we might as well do this using just the simple shapes. And so that's how we're going to do that. The area of this is just 1/2 of the base times the height. The base is 3, the height is 2. So 1/2 times the base times the height is 3. The area of this is half of the area of a circle. So it's just 1/2 pi r squared, which is 2 pi. So that means that the area of the definite integral is just this area plus this area, but this area, which is under the x-axis, is going to be a negative area. So it would be 3 minus 2 pi. So that's how we calculate the definite integral by definition. You should find the area between the curve and the x-axis. And notice if the curve is above the x-axis, the area is positive. If the curve is below the x-axis, the area is a negative. Okay, now we get to the very important, the major theorem of this part of the course, which is the fundamental theorem of calculus. It basically ties together two things that we learned, differentiating and anti-differentiating. And this theorem basically tells us that those two operations are inverses. One reversed the other. So let's talk more about that. So first of all, let's make a definition. Let's say I have a function, f. Let's make it f of t. So t is the variable here. There's a reason for that. So this is a little f of t. And let's define a new function called g of x. And g of x is it's just going to be the area starting at a. G of x is the area under f starting at a all the way to x. Notice x here has a different interpretation than the variable here. So that's why we don't want to call this x, because we want this to be t. T is the independent variable. And g of x, but given an x, so x is given a fixed x, g of x is the area under f of t from a all the way to x. It's the area of this region right here. So again, given a function f, we define a new function, and this new function is the area function starting at a and ending at x. So let's do some example here to make sense of this. So let's say this is f of t, and we're going to define g of x to be the definite integral from 0 to x of f of t dt. And so again, this is just areas. And so this function is made so that it's simple in the sense that we can just find areas on the curve fairly easily. So for example, g of 0. G of 0 is the integral from 0 to, if x is 0, then this is the integral from 0 to 0. The integral from 0 to 0 is the area of a point, which is 0. What's g of 1? Well, g of 1, again, by definition, using g of x here, is the integral from 0 to 1. So again, x is now 1, so you replace x with 1, and now g of 1 is the area under the f from 0 to 1. So again, the g function is just the area starting at 0 and then going up to a certain x. So g of 1 is the area from 0 to 1. So the area of the triangle, 1/2 base times height, this area is 1. So g of 1 is 1. Same for the rest. G of 2 is the area starting at 0 up to 2. So this number here tells you where to stop. Right? This definition of the function starts at 0. Whatever value x is the area under f, right, from 0 up to that point. So the area from 0 to 2 is the area of the triangle plus the area of the rectangle. So it's just 1 plus 2. So this area is 3. So g of 2 is simply 3. It's the area from 0 up to 2. Same for the rest of it. G of 3 is the area from 0 up to 3. This one you have to approximate a little bit. It's not exactly right. And then G of 4, notice this positive area and this negative area cancels. So these two areas cancel. And so G of 4 is just 3 again, because this is 3. Again, we are kind of assuming here that these two functions are roughly the same. If they're exactly the same, then it perfectly cancel. But even if it's not exactly the same, you can approximate that these basically cancel. And then g of 5 is the area from 0 up to 5. So again, you have to do a little bit of approximation. But the whole point of this is that g of x is defined to be the area under the f function from 0 up to x. So if I were to graph it, it looks something like this. Right? This is the area. This function, again, represents the area function under f. Okay, so here comes the fundamental theorem of calculus, part 1. There are actually two parts to this theorem. Part 1 says that if I define this function g of x as the area from a to x under f, then something that nice that happens is that when I differentiate g, I get f again. I get the little f again. So this says that if g of x is defined to be the definite integral from a to x of f, so and I differentiate that, I get f again. In other words, the anti-differentiating or taking the definite integral up to x is kind of the reverse of differentiating. Because if I anti-differentiate and then differentiate, I get back to the original function f. So again, anti-differentiate, differentiate, cancels out. Kind of like multiply and divide, cancels out. If I multiply by 8 and divide by 8, I get back to what I had earlier. If I add 7 and minus 7, I get back to what I had earlier. If I integrate and then differentiate, I get back to the original function I had earlier. So this is the major theorem of calculus. So for example, here's the g of x function defined to be the integral from 0 to x of this function. If I use that theorem to differentiate this function, if I differentiate g of x, I should get back to the original function. This function inside here, this is f of t. But I should get back, notice I get back not f of t, but I get back f of x. Because the g of x is a function of x. So differentiating should give you a function of x. So differentiate g, I should get back this f function here, but it has to be a function of x. So I replace everything here with just x. So root of 1 plus x squared. Alright, here's the second part of this theorem. So the first part says that if I integrate and then differentiate, it cancels. The second part tells us how to evaluate a definite integral from a to b. Remember earlier we said that this definite integral is an area problem. And so the second part of this theorem tells us how to find this area, how to find this definite integral. And this basically tells us how to compute it. It's very simple. It says that to find the definite integral from a to b of f of x dx, in other words, to find the area from a to b between f of x and the x-axis, I find one antiderivative. I find any one of them. Pick any plus c you want. So find one big F, and then plug in the endpoint b and a and subtract. So this is this shows how to find this definite integral. And notice that on the left side here, this is a calculus problem. This is the area under a curve, which is very hard, but this theorem makes it very easy. It says that find any antiderivative, which we know how to do from earlier, plug in the endpoints a and b, subtract, and that is exactly the area between the x-axis and f of x. So the right side is very simple to do, the left side is very hard, and this theorem allows us to calculate this hard problem of an area under a curve with something much easier. So how do you find the definite integral from 1 to 3 of ex? Well, all you need is just one antiderivative. And we know that this is very easy. The antiderivative of ex is just ex again, because when you differentiate ex, you get ex. So this part 2 of the theorem says that to find this definite integral, I take the antiderivative, I plug in the endpoints, 3 and 1, I subtract. And this expression is exactly the area under this curve from 1 to 3. Notice that this theorem says I can use any antiderivative. I can pick any constant I want. For example, instead of picking EX, I can say EX plus 7 or EX plus C. Turns out that doesn't matter because if I do EX plus 7, there's a plus 7 here. When you plug in, there's also plus 7 here, so the 2 will cancel out. So it doesn't matter which plus C you pick. The difference here will cancel it out anyway. Always get the same answer. Here's another one. If I want to find the area, this is actually the original problem we had a while back. To find the area, at the very beginning, we want to find this area. Yeah, that's just the definite integral from 0 to 1 of x squared, but we didn't know how to do it before. Taking this limit process, right, we don't know how to do that, but we know how to do that using the theorem here, which says that to find the area under the curve from 0 to 1 of x squared, all I have to do is find one antiderivative. So notice one antiderivative of x squared is just using the reverse power rule, add 1 divide x cubed over 3. So take that antiderivative, plug in the endpoints. Plug in 1, subtract, plug in 0, and you get 1/3. By the way, this is a simplifying notation. It's just a shortcut. This notation just says that pick one antiderivative, pick any of them. This notation just says that once you pick it, this just means that you plug in the top, plug in 1, minus plug in 0. That's exactly what the theorem says. Plug in the top, plug in the bottom, subtract them. So this notation is just an intermediate step to know what is the antiderivative, and so that when you plug in the 1 and 0, you know what to plug in. So now we know how to find, we just found out the area under a curve. That area is exactly 1/3. Here's another example. Again, to find the area under the curve or the definite integral, I just find one antiderivative, in this case ln of x, absolute value of x, but everything here is positive, so I can just drop the absolute value. So again, using that shortcut notation, I pick one antiderivative, which is ln of x, and then I plug in the endpoints and subtract. Plug in 6 minus plug in 3. So again, this notation means that I plug in 6 into this, plug in 3, and I subtract it. So this allows us to find definite integrals very simply. You can use some algebra to simplify this, by the way, but so for example, the difference of the log is just the log of the quotient. Yeah, so we can find do a more complicated example, finding the area under the cosine curve. Turns out this area is 1, as we can check right now, which is surprising, right? It doesn't look, this function is kind of complicated, but has a nice area of being 1. Yeah, so we need to find the integral from 0 to pi over 2 of this. And so notice that one antiderivative of cosine is sine. So all I have to do is plug in the endpoints. Plug in pi over 2, plug in 0, and subtract. Sine of 0 is 0. B, right? B in this case is pi over 2. Sine of pi over 2 is just 1. So now we know how to find area under curves. We know how to find these things, which is called the definite integral, just the area under the curve. Yeah, so as I mentioned earlier, right, so the fundamental theorem of calculus has 2 parts. Part 1 is not, realizing that integrating then differentiating gives you back the original function, so the inverses. Part 2 says that to find a definite integral under a function, to find the area under the function, we find one antiderivative, plug in the endpoints, and subtract. So another way to write part 1 here is that if I integrate and then differentiate it, it cancels. I get back the f function again. But the f function is not a function of t, it must be a function of x. And then another way to, well actually let's kind of talk about that over here instead. Alright, this is basically the last section of the course. We'll talk about the net change theorem and indefinite integrals. So earlier we talked about definite integral. Definite integral is just the area under the curve, and we learned from fundamental theorem calculus that you can do definite integral with these bounds are just constants by using the fundamental theorem calculus. So this is definite integral. We can evaluate them now. But this theorem is about indefinite integral. Indefinite integral is essentially the same thing as the family of antiderivatives. So notice this is also the integral symbol, but there's no endpoint. There's no a, b. There's no bounds. This is why it's called an indefinite integral as opposed to a definite integral. So the indefinite integral of f of x dx is just simply f of x, where f of x is the family of all antiderivatives of little f of x. So for example, what is the indefinite integral of x squared? Well, find the antiderivative, x cubed over 3, just the reverse power rule, add in the plus c. So this family of antiderivative is exactly the indefinite integral. So here's an example. What is the general indefinite integral? You just do them separately. The left side is just the power rule, x to the 5th divided by 5, which is 2x to the 5th. And you remember that if you differentiate tangent, you get secant square. So therefore, 2 tangent must be the antiderivative of this expression. And so we have the family of indefinite integral 2x to the 5th minus 2 tangent x plus c. If I differentiate this, I should get this again. So again, this indefinite integral is simply the antiderivative. I notice that should make sense because we saw earlier that to find the definite integral involves an antiderivative as well. So this is definitely related. And then one thing I want to point out is that if you want to find indefinite integral of anything that involves power rules, it's always better to multiply everything out, simplify, and then apply the power rule individually. And because we already know how to find antiderivative with power rule using the reverse power rule, remember add 1 then divide by that exponent, we can find the antiderivative of these 3 components by doing them separately by applying the power rule. So for example, x to the 3/2, add 1 is 5/2, divide by 5/2 is 2/5. X to the 1/2, add 1 is 3/2, divide by 3/2. You flip the this to 2/3, and then you can cancel. And then you get 4/3. X to the negative 1/2, you add 1, which is 1/2, divide by 1/2, it's the same thing as times 2. So that's how you can find indefinite integrals. Yeah, so this table is really not different than the table we showed earlier, which is the table of antiderivatives. Again, indefinite integral is the same thing as the family of antiderivatives. Again, if you know how to differentiate, you know how to anti-differentiate. So really, this table is really no different than what we saw earlier, finding anti-derivatives. Again, some of these are not covered in the course. Hyperbolic stuff, for example, the bottom here is not covered. But all these things we've seen before. If you know how to differentiate, you know how to anti-differentiate. Just thinking backwards. A couple of things to point out is this is the reverse power rule. Add 1, divide by it. This one is just ln of absolute value of x. So again, some of these you have to memorize. These comes because if we know how to differentiate these on the right, so we know how to anti-differentiate. If I differentiate tangent, I get secant square. So anti-differentiating secant square gives me tangent. And then one last thing I want to point out is this is called the net change theorem. This is the same thing as the second part of FTC, the net change theorem is the same thing as the fundamental theorem of calculus part 2. If I want to find a definite integral, I just find an antiderivative and plug in the endpoint and subtract. But it has it's kind of phrased as a way to to solve some application problem. And so the way it's phrased is that, again, at the top, this top part here is exactly FTC part 2, but instead of writing f, you write f prime of x, where big F prime of x. Because big F, if big F is an antiderivative, then when you differentiate big F, you get little f. So rewriting this as big F prime gives you the same, again, this is exactly the same thing as this, just doing a substitution. This is the same theorem, but we call this the net change theorem because it says something very simple. It says that if I integrate from a to b of f prime, I get the difference of of f of b minus f of a. And so if you interpret big F prime as the rate of change, this says that the integral of the rate of change is the net change. This is why I call it the net change theorem. So again, if so for example, if big F is the population, big F prime is the rate of change of population, and this says that the integral of the rate of change of population is the net change in population. It turns out that this is actually not going to be tested on your final. It's actually not even in the homework, but this is actually a very useful theorem. So for example, if you know the volume of water in some kind of a tank, V of t, but let's say that V of t is unknown. We don't know the actual volume function, but we know the rate of change of the volume, how fast the water is entering your tank or your reservoir. That's V prime of t. And so this theorem is useful because if I know V prime of t, if I know the rate of change, I can get the net change. So the integral of from time 1 to time 2 of the rate of change of the volume is the change in volume. So this says that if I integrate the rate of change, I get the net change. And this is very useful in general because if I know population, typically in many applications, we don't know the function itself, the modeling function. We only know how fast it's growing or how fast it's changing. So for example, if I know the rate of change of population, I can integrate to get the actual change of population. Okay, that's it for this week.